Assalamu alaikum dear friends. Welcome to the lecture of the quantum mechanics. In this lecture, we will discuss the solution for the problem number 3.19, which says that consider a system with whose state psi at later function t is given, psi at later time is given this, and two variable observable a and b are also given. So the question state requirements are: if I maximize and center it, the first part is, are A and B compatibles? Which among these set of operator A, B and AB form a complete set of computing operator? And then measuring A first and measuring B after that, we have to find the probability of obtaining value of -1 for A and value of 3 for B. Similarly, measuring first B and then A, then find the probability for obtaining 3 for B and -1 for A. Compare this result with the probability obtained in part B. The very first thing is we have to check the compatibility. Means we will check that whether our two operators are compatible or not. A and B, AB is equal to AB minus BA. We are given with the A operator and B operator, A operator and B minus B and to A. If this is equal to 0, it means they are compatible. But results show that these are not coming equal to 0. It means our A and B are not compatible, and they do not commute and do not form a complete set of commuting operator. They do not have common set of eigenstate. In the next, for the probabilities, finding the probability for obtaining a value of -1 for A and value of 3 for B, mean first we will find the eigenvalues and then the probabilities for that states. So if we for A solve for A, then you will use a secular equation, determinant of A minus lambda I, that will be equal to 0. And similarly, for if we expand, we are given with the value of A minus A. So A operator minus A is eigenvalues and I is the identity matrix. For example, if it is 3 by 3 matrix, so this will be 0 1 0 0 0 and 1. Okay, I think you will be familiar with these equations and how to solve this for eigenvalues. This will give A1 is equal to 2, A2 is equal to -1 and A3 is equal to 0. So the spectrum of A is not degenerate because no eigenvalue is going to be repeated. Okay, and A form a complete set of commuting operator. Similarly, determinant for the B operators, we will write the secular equations for finding the linear independence values, and this will also give some eigenvalues. If I centered it, it will give eigenvalues which b1 is equal to 3, b2 is equal to this, and b3 is equal to this. The spectrum of B is not degenerate, due that no eigenvalues is going to be repeated. It means they also form a complete set of commuting operator. If eigenvalues not degenerate, it means they will form a complete set of commuting operators. Now we will go for the probabilities of A and B. If we find the eigenstate for the first set of eigenvector of the operator A, which is you know that if you are given with eigenvalues and observable, you can find the eigenvectors like this: Ax is equal to lambda multiplied by x. So x is some unknown matrix which is xyz, and similarly we have x which is unknown, lambda is the eigenvalues which is 2. For example, we take first value for observable A. So we can solve this by matrices elimination method or any Gauss-Jordan methods or any others which are reduced echelon and as we can find this eigenstate A1, which is normalized eigenvector for eigenvalues 2, and this is similarly we repeat for the other two eigenvalues because we have 3 by 3 matrix. Definitely we will have with 3 eigenvalues, and for the second eigenvalues which is equal to -1, as you are observing here, -1. So if we solve this for eigenvectors, this will give us By centering it, it will give us a2 is equal to 1 over under root 3 1 iota minus 1. Okay, this is the eigenvector for second eigenvalue. Similarly, we can proceed for the third eigenvalues, which will give vector normalized eigenvector a3 is equal to this. And laterally, the same procedure can be repeated for the observable b to yield eigenvector b1, b2 and b3, which is not different from the above one. And since they are not commuting, the operator do not have the common eigenspace. You can compare the values of a1, a2, a1 with the b1, a2 with the b2. They will not, both are not similar. If we compare the values of a1 with the b1, they are different because their eigenvalues corresponding to observable are different. And for the probabilities, now we can find the probability for measuring values 3 of observable a. We have that probability of any observable is equal to a n psi modulus square divided by normalizations. So for psi and psi, because we are given with the psi, so psi cat and psi bra, because psi, if we are given with the psi, so we can find its cat by taking the complex conjugate the above matrices. So all the cats will be converted into bra, and then multiplying this will give us 1 over under root 3 row vector and multiply by column vector, so it will give us 5 over 3. So probability for 1 is equal to a1 psi modulus square and psi and psi. Psi, and we are given with psi and psi. Okay, a1 and psi. a1 is the eigen vector which we have already found out, and psi is the given state at later time. So we take the row vector from a1 for a1 and column vector for psi, so it will give us probability is equal to 8 over 45 after solving some steps. And similarly, probability for b with the given eigenvalues, we have our system in the state corresponding to eigenvalue 3 for the observable b. Okay, this means that the probability of finding the observable b in the state -1 will be given is equal to probability of b1 is equal to b1 a1 modulus square. We are given with the b1 because because probability for b1 eigenvector is -1, so we will take b1 and a1 modulus square, which will equal to b1 is this and a1 is this. Take its modulus square, it will give us probability 2 by 3. So we because the two are mutually independent, the total probability in this case will be equal to product of the two probabilities, because if we find observable a and then observable b, these two are independent events, so their probability will not affect with each other. We can multiply for the total probability for one and probability for the second. Okay, so this will give us 16 over 135. Again, for the second case, next we repeat the procedure, but this time we measure observable b first. Probability for b1 will be equal to b1 into psi modulus square psi and psi. You know b1 is given, psi is also given, and we can find probability for b1 which is equal to 1 over 15. And similarly, our system in the state corresponding to the eigenvalues -1 of the observable. This means that the probability of finding the observable in the state 3 will be given to a1 and then b1 whole modulus square as by definition of probability. So this will give us 2 by 3. Again, finding the probability, total probabilities of the independent event, which will be the product of the probability, and it will give us probability of a1, probability of it, which is equal to 6 over 135. Okay, so we have found out that total probability in the first case and total probability in the second case 16 over 135, and the second case we have probability 6 over 135. It means both probabilities are equals. So finding observable a first then b or b first then a does not influence the our findings. It means both have commutable compatibles.